This is the first geometric proof that I drew back in August of 2015. So let's get started. Basically what we're going to do is establish a square, certain perimeter size square, draw the golden ratio, get Kepler's golden ratio right triangle, and then be able to draw the circumference, etc. So let's start off with the blue circle here is just a given circumference of 2 units. Roll it across P1, P2, P3, and you've rolled the circle one time, and that distance from here to here is just a given 2 units, arbitrary, we made it up. Drop that 2 units down to the top of a line, YH, 2 units, and go ahead and draw the square. 2 units, 2 units here, 2 units here. So we have a square YHWT, back to Y, of 8. That's the size of the perimeter of this square. The next thing we want to do is divide this square, YHWT, into 4 equal inside squares, each 1 unit. 1, 2, 3, 4, 1, 2, 3, 4. Each one of these are equal. Then we want to extend one of the squares, the 1 unit squares, out some more, another 1 unit, in order to create a rectangle FBJA. Why do we want to do that? Because we want to create the golden ratio triangle 1, 2, square root of 5, the number 5, because 1 plus the square root of 5 over 2 is equal to phi. How do we find geometrically phi? It's on the web, it's in many textbooks. First we draw the diagonal of this 1, 2, square root of 5 right triangle, AB diagonal. Find the midpoint here at M, it's exactly equal to halfway. And draw a 1 unit diameter circle, and where that circle crosses the diagonal AB at C is phi, the golden ratio. C to B is the inverse of phi. We did that so that we could swing phi up to this line and hit this line like it's a radius, and this is also phi. So since this is 1, this is phi, this side must be Kepler's third side of his golden ratio right triangle, the square root of phi. Dropping FE, which is the square root of phi, down to the diameter of what is going to be this large yellow circle, we see that this distance from A to I is the same as the distance from F to E, which is Kepler's square root of phi. So we note that each of the blue circles whose circumference is 2, 4 of them fit tangent to each other across the diameter of this big yellow circle that we drew with a radius of equal to the square root of phi. Diameter equals 2 times the square root of phi. And since we know the circumference of the blue circle, we now know the diameter of each blue circle, which is 1/2 of the radius, which is square root of phi, so it's 1/2 square root of phi. And we can compute pi. If you set up the equation, pi will equal, reduces to 4 over the square root of the golden ratio. The second thing we want to do is note that we can draw double the blue circumference and diameter and make C1, which is the same as the blue circle, equal to C2, this circle here. Triple the blue circle's circumference and diameter, and we have C3. Quadruple it, which accounts for the 4 circles across the diameter, and we have the big yellow circle. So since we know what pi is from calculating here each blue given circle, we can multiply the diameter of the big yellow circle here, 2 times the square root of phi times pi, which we discovered was 3.144605511, and we get the perimeter of this big yellow circle, which is 8, which is the same as the perimeter of the square. 8. 1, 2, 3, 4, 5, 6, 7, 8. So you could put this blue circle on the edge of the giant yellow circle, roll it one half a revolution, and it's 1. From here to here is 1. Complete the 1 revolution, and that's 2, just like we defined. That's 1/4 of the circle. You see that this is 1, that's 1. From P1 to P2 is 1, P2 to P3 is 1. 4 times that will equal the circumference, which is 8. So that's the first proof, geometric proof, showing that the true pi is not equal to the old pi. And as you've seen before in measuring physical measurement of a 1 unit diameter pi circumference circle, pi equals 3.144605511.